very happy to be here, and we're talking about the future of cities. We're talking about el futuro de la tecnología, but today we'll bring you into the past. So, how many of you have been to Paris? Okay. So some people that has been to Paris 100 years ago, in 1901, tried to imagine the future of Paris in the year 2000. It was a group of artists, and they wrote some postcards, some pictures. So Paris in the year 2000 would look like this. So for example, they well predicted the technology entering agriculture. They predicted very well technology entering our homes. This is the first Roomba in history. But then they thought that, flying police, flying firemen, or buses attached to whales. So first lesson that we can learn from this: never predict the future. You get something right, you get something wrong. So what they didn't get? What did they miss? So first of all, they missed this: the prominent role of cars in our cities, in our society. But most importantly, they missed this. So this is the city of Lisbon, seeing in real time through the data from their transportation system. The fact that today we can study cities as living organisms, as complex systems, simply because we have so many data that are produced by cities, by citizens, and we can understand new layers on how these cities work and function. And this is exactly what we do at the MIT SENSEable City Lab. We try to understand the two layers of cities, the physical layer and the digital layer, how we can recombine them and understand what's in between. So this is our small place at MIT. In case you haven't come to Boston, we would be very happy to welcome you there. And I'll show you some of the projects we've done in the past years on this. And I'll start with New York in 2014. It was the first time that the mayor had released the data from the taxi systems. So in this picture, every yellow point is a taxi pickup, someone getting on a taxi, and every blue point is a taxi drop-off, so someone getting off a taxi. This is a very particular place in New York City. Can anybody guess where this place is? The airport, very good, JFK. If you zoom out, you see the whole city. So this is 1 year of data, taxi activity in New York in 2014. We are planners, we are mathematicians, we are physicists, we are biologists, we start counting. So how many people take a taxi from one point to the other in 1 year? And those are real numbers. We had fun to play around, including counting how many people take a taxi from one corner to the other of the same block. New York City, New Yorkers are very lazy. But as trips are so dense, there are so many people moving from one point to another, we said, does it make sense to share some of these trips? If myself and you are going to the airport, can we have the same taxi picking me up, picking you up, and then go together to the airport? Is it feasible? So it turned out that at that time we had data like this, but we had no system for giving an answer or creating a real service. So we had to use new types of mathematics. We used shareability networks from the network theory. We published a paper, and we proved that more than 95% of New York taxi trips can be shared. And this is a huge number because it really proves the fact that people, if are willing to share a car, it's possible, if it's feasible, it's profitable. And every time two people share the same taxi, you virtually take one car out of the city, meaning less congestion, less traffic, less pollution. The future is history. We got a phone call from Uber. Uber decided to implement this. Uber Pool was created. And we know that in some of the main American cities, especially before COVID, we had more Uber share, Uber pool trips than normal Uber. So this is just an example on how some small technological change, some small algorithms can really change a service in the cities. But let's look at the future. Let's look at autonomous mobility. The fact that with autonomous cars, not only the car will change, not only everything that is around car, insurance, services could change, but also the physical city. For example, this place in the road, intersections. So intersections are a very interesting part of the city because two cars compete for the same space. We normally solve this problem with traffic lights. This is the first traffic light in history. In the future, where cars will be able to communicate within each other, are going to be able to coordinate, and a road intersection would look like this. Don't try it yet. But it's interesting to understand and to realize, does this make sense? So we tried again to simulate what is the average waiting times compared to a normal intersection, to a new type of intersection, and most interesting, what is the pollution that we get? And we see that in both cases, for example, we get much better results in terms of reduced waiting times for traffic, but also reduced pollution, because cars don't need to stop and go, but simply decelerate and accelerate. But then what happens to the other parts of the city? For example, parking lots. So today, you buy a car, and you use it only for 5% of its time. 95% of its time, your car is empty, parked. So not only you don't use your car, but your car is using some very valuable real estate in the city. So most of our cities is just for empty cars, to the point that our buildings have been built with this in mind. You have space for people, and you have space for cars. Well, in the future, this number could really change, right? So we have done some studies in Singapore. In Singapore, today, this number of cars, in the future, with shared mobility, with autonomous mobility, we might have a reduction of number of cars, like this one, and the same car that brings me to the office in the morning can go and give a ride to anybody else in the city, and maybe be parked outside of the city center. And so in Singapore, if this is the number of today's parking spots, this could be the number in the future. So imagine what can you do in a city with 70% more space that today was used just for parking spots. But can we use cars in different ways? Not just for bringing people from one location to another of the same city. Can we use cars as a sensor? And for sensing what? I'll tell you a short story on bridges. So bridges are getting old and old. We have had some problems of bridges in history. Every engineer in the room would recognize this one, this Tacoma Bridge. In the 40s, it eventually collapsed. If you read the news some weeks ago, this happened. But I'm not talking about this. I'm talking about this. This is the bridge in front of MIT. At one point, they realized that there was a crack in the bridge, and they discovered that the crack was actually quite serious, and they had to close the bridge for several years, causing a lot of discomfort and damage to the city because it basically broke the city in two parts. So why is this happening? Because today we check bridges in a very low-tech way. We have people going and visually inspect bridges, and if it looks good, it's normally good. Can we do better? Well, we know that every bridge vibrates. That's totally normal. It's good that a bridge vibrates, but if the vibration changes over time, that's not good news. Vibration is kind of like a fingerprint of a bridge. So monitoring the vibrations of bridge, we can tell a lot about their health. How do we measure vibrations? Accelerometers. It's a physical sensor that measures vibrations. And some of these accelerometers are installed in some major bridges. This is the Golden Gate Bridge in San Francisco. There are dozens of sensors like this. They collect accelerations constantly, and they're able to tell if the Golden Gate Bridge is healthy or not. Great, amazing technology, very expensive. If you want to equip any possible bridge with this technology, you're going to spend billions of dollars. So it's not scalable at all. So we had a crazy idea in the lab saying that, hey, there is an accelerometer here as well. So can we use cell phones that drive every day on bridges on board of our cars? Does it work? We tried it out. So we installed some cell phones on a car. We went on the Golden Gate. We drove back and forth, just to acquire enough data until we got stopped by the police, but that's another story. We went back to the lab, analyzed the data, and bingo, it is possible to understand a bridge vibration and take it out from the car's vibration. We acquired some more data, we published some papers. We started a big collaboration with the Italian Road Authority. We built an app for them. So their workers, in their normal maintenance work, in their bridges, in their streets, they record data from bridges. Those are the bridges that we are monitoring in Italy. And the goal is having a small digital twin for each bridge, so that if there is something wrong, they immediately send an engineer to really inspect it. It's like a red light that should alight if the data are not good enough. And then an expert, a real bridge expert, goes and checks. But is there anything else we can scan in the city? Maybe some hidden layers, some things that we don't see. For example, this is the air quality in New York. So air quality pollution really changes meter by meter. It's something we don't see, we don't really realize, but if you look at the numbers, you can have very good air quality in one part of the city, and just some meters away, very bad air quality. It depends on the wind, it depends on the vegetation, it depends on how the city is built. The problem is that we don't see it, we don't realize it, and it's very hard to measure. So how do we normally measure it? Fixed sensors, very good, very expensive, but they only measure the air quality here and not there. Or satellite measurements, but are not very fine-grained. The resolution is not enough. So we designed a small sensor, modular, that we can attach to a vehicle, any vehicle. It's solar-powered, it's totally automatic, and it collects data. This is a great way to collect data meter by meter using the normal existing infrastructure. We've been using taxis, we've been using trash trucks, we've been using police cars without paying for drivers. And it collects a lot of information like images, thermal images, and of course, air quality. And what is the result? Is something like this, maps. Maps that anybody can use. People were willing to understand the air quality at their doorstep, city administrators, or other companies that can build products and services on this. And this is now a modular platform, so anybody can add their sensor, and it's also open source, so that anybody can build it. We have done different deployments in different cities, and every city has a different question. Some is interested in air quality, some is interested, like in New York, in disparity, socioeconomical disparity when we're talking about air quality. Some, like Stockholm, are interested in heat, in if we can measure the heat bubbles, the heat islands, the fact that some parts of the city overheat with respect to some others. But then sensing the invisible, can we also sense the informal? Can we sense parts of the city that nobody senses? I'm talking about this. So this is in Brazil. I was there a couple of weeks ago, And it's what people call slums, shanty towns. In Brazilian, they're called favelas. They are informal settlements where there is basically no regulation, people just build for their survivals. The police doesn't go here, there is no formal planning, and gathering data from these parts of the city is nearly impossible. It's not a small problem. It is estimated that 15% of the global population live in this kind of settlements. 15% of the global population. You know that cities are rising. Urbanization rate is 1.7%, meaning that every 2 months we have a new London, okay? This London every 2 months is probably more similar to this than to London, okay? The fact that today we pose all our energy into planned cities means that we are probably missing one of the big elephants in the room, which is this kind of settlements. And you have diseases here. This is another favelas in Brazil. And you might wonder why people build on the left, on the right, and not in the center. Well, the problem is that it's slided away. So there are so many things that in normal cities we plan, we forecast, and we avoid, and in this kind of uncontrolled growth, it doesn't happen. So we said, why don't we get data in a different way? Pictures there, of course, not allowed. Don't go there and take a camera, they would kill you. Don't fly with a drone, they would shut it down. So we use LiDAR. LiDAR is laser technology that takes the volume of buildings, but doesn't take the face of people. So with some local organizations, we've been there explaining what we were doing, and for the first time, we built a 3D model, a 3D representation of a favela. Have that, you can use intelligence, mathematics, to measure, to estimate, to understand what's there, to do simulations, to map the incredible complexity of that environment, to understand, is it dangerous, is it not dangerous, what should I need to modify, what are the surgical interventions that I can do to buildings to avoid cholera, for example. Can we build and can we create new property titles for these kind of environments? Well, it all starts with data. So being able to have good data is the base for any possible service on that. And let me wrap all of this up with a final project, adding everything that I talked about: mobility, autonomous mobility, sensing, and inaccessible places. And with this final example, I'll bring you to Amsterdam. So if you've been to Amsterdam, you have realized that you have more water than roads, more canals than streets. And when the city mayor asked us to reinvent the mobility in Amsterdam, we said, great, it's going to be electrical, it's going to be autonomous, it's going to gather a lot of data from the city, but it's not going to be a car, it's going to be a boat. And so we created this concept of autonomous boats, which we called rowboat, which is a small vessel, autonomous, that goes around in the urban canal. We are at MIT, we had to prototype things, we did everything in-house, understood which technology to equip these little boats, we trained them on how to autonomously navigate. This is the MIT swimming pool, by the way. There are no people swimming, only robots. We had to teach them how to avoid obstacles, how to autonomously latch together or dock at the pier. And after 5 years of R&D, that's the final result. So it's a fully autonomous level 5 boat that goes around of course, service the city with people transport. If you go to Amsterdam today, you can try one of these. But most importantly, serves other city needs, like trash collection. So same technology, same platform, just a little tweak in the configuration, and you can carry out a city service. And you can go on and on in thinking of this not as boats, but as floating pixels, autonomous pixels, that can get together and bring life to new types of urban environment, like an open-air market, or like a bridge, whenever there is an emergency, whenever you are expecting a lot of people, you can order these boats to come together and bring life to a new piece of infrastructure. So I'll stop here. I hope that you have seen some of the new technologies that are in cities, but most importantly, the fact that each city is unique, and everybody of us together, from the different sectors, from the different communities and disciplines, can make this life possible. Thank you very much.